We're going to look at the alternating series. Okay, good. I think that just says we're recording now. So our objectives today are students will be able to determine if an alternating series converges or diverges, so that's kind of what we've been doing. We're also going to use the alternating series remainder theorem, basically, to approximate sums. And we'd also like to be able to classify if a series is either absolutely or conditionally convergent. Okay, so there's actually quite a bit on today's lesson, and I'll try to go through it fairly quickly. Before we go to the first slide, I'd like you to think about, so I think we've talked about series, we've talked about series in section 8.2, section 8.3, and section 8.4. So these were the comparison tests, I believe. Section 8.3, if I'm not mistaken, I think that was the integral test in the P series. I think that's right. And then in section 8.2, we did the geometric series and the telescoping series, right? So far, those are some of the things that we've discussed thus far. Here's the reason I'm bringing that up. Guess what one of the main requirements is for most of those, not quite all of them, but almost all of those convergence tests? They have to be greater than 0. On most of these, the requirement is that the a sub n is greater than 0, right? Okay, so what happens when you get something like this, or like this? So here you can see clearly that we have terms that are not positive. In fact, we have not only just a few terms that are not positive, we have infinitely many terms that are not positive. So you cannot, and I'm just telling you right now, this is an example of, you will not have the freedom of saying, hey, by the direct comparison test on any of the problems today. Any problem that we see today involving an alternating series, the direct comparison test requires that those values be greater than 1. I'm sorry, greater than 0. So how are we going to do that? The good news is it's actually not very difficult. It's actually pretty simple. By the way, this is called the alternating harmonic series. You can probably see why that is. This one's close to the alternating harmonic series. It's just kind of missing the first term. Notice, though, that the first term here is positive, then negative, then positive, then negative. The one below that is negative, positive. So alternating, in other words, it's flipping sums. We see from these examples that the nth term of the alternating series is of the form, it's either -1 to the n minus 1 times bn, or it's -1 to the n. In fact, there's actually other ways we could write it as well, where b sub n is positive numbers. So notice, if I go back to here, n is still 1, so these are going to be positive. The only thing that the -1 to the whatever power is contributing to this is whether the term is positive or negative. The following test says that the terms of an alternating series decrease towards 0 in absolute value. In other words, they're converging from above and below. See, everything up to this point, we've assumed that they're all above the x-axis. So as the series continues, we're getting closer and closer to the 0 from the top. In an alternating series, we're doing the absolute value, so we're actually coming in from the top and the bottom. Okay, important slide right here. By the way, this is very similar to the one that you had in the notes that I did in the YouTube video that I posted last Friday, except I think in that video, I think I used a sub n. And I think possibly these were switched around, but guys, it doesn't matter. Those are the two conditions that you need. So if you have an alternating series that can be written in this form, where we've got the alternator, if you will, right there, that's the thing that's determining if it's positive or negative, times some b sub n, we've been talking about those b sub n's, and it satisfies these two things, that the next term is less than or equal to the previous term for some n, and that the limit of the nth term goes to 0. Now notice that both of these conditions have nothing to do with that alternator. Let's look at an example. says determine if the alternating harmonic series converges. Now, if I'm not mistaken, I think we just talked about the harmonic series, and it does what? It diverges, correct? In fact, I even mentioned that I thought it was one of the most important divergent series. So let's see if it converges. What's your gut instinct? That it converges? Okay, so Jack thinks it does. So let's see. So we're just going to go back here to this alternating series test, and you'll often see me abbreviate that as AST. And so here's what we need to figure out basically. Is, and I'm going to write A sub n, is A sub n plus 1, and we need to be very careful. We want to show that the next term is less than or equal to the n term. And then 2, oops, wrong way. We want to see if the limit of that thing, so A sub n, the limit as n goes to infinity, if that's equal to 0. And I think we've kind of already talked about this guy. Does anybody happen to remember what we call something we've done in the recent past whenever we look at the limit of the A sub n term equaling 0? The important theorem. I'll give you a hint. If this doesn't equal 0, what does that imply? The series has to diverge. That was our divergence theorem. So similar, obviously not exactly the same, but let's go ahead and keep going. So basically what we're doing here is we're making sure that we're adding zeros at the end. I mean, if we're adding something non-zero, then by that divergence theorem, it's going to diverge. So let's go ahead and put it. By the way, I think in the notes I did on the YouTube video, I think this was actually the first criteria and the second. Again, I don't care. All right, let's do the limit thing first, though, if you guys don't mind. We need to do the limit as n goes to infinity, and in this case, remember we're talking about the alternating harmonic series. This is the alternator. This is the only thing, that thing up there in the top, that -1 to the n minus 1. The only thing that's doing is making it positive or negative, positive or negative. That's all it's doing. A sub n, in fact, maybe I should make a note of this. A sub n in this problem is 1 over n. This up here, that's that alternator. Okay. I mean, okay, that was easy. Clearly that goes to 0. So if we went all the way back to section 8.1, when we were talking about sequences, if we got rid of these pluses or minuses, does the sequence of 1, 1/2, 1/3, 1/4, does it converge? The answer is yes. That sequence does converge. The series, though, does not. Did you hear what I said? Let me say that again. The harmonic sequence converges. The harmonic series diverges. We're going to try to figure out if this alternating harmonic series converges or diverges. So far, we've met the first criteria. In fact, we'll do that in green. Check. Great. Now let's do the second part, which you already seen me do kind of in the warm-up here. We just need to show, is the next term less than the one before it? Yeah. In other words, is 1 over n less than, is 1 over n plus 1 less than or equal to n? So if the n term is 1 over n, the n plus 1 term is 1 over n plus 1. Now we'll just cross multiply, subtract n on both sides. Both conditions have been met. Therefore, the alternating harmonic series converges by AST. That's your answer. Now, guys, I'm just going to be completely honest with you. That just seems to not make sense, doesn't it? We just said the harmonic series diverges. But it turns out that the alternating harmonic series converges. I'd like you to think about why that actually makes sense. If you think about it. Why might that make sense then? Anyways, I'll let you ponder that. That's probably a better question for me not to answer right now. Does anybody have any comments or questions on my first example here with the alternating harmonic series? Okay. All right. So let's go ahead and move on. Let's look at another example. Converge, diverge. I don't know. Let's see here. Okay. Can you see the alternator? So you see the alternator. There it is. So what's A sub n going to be in this problem? Yep. Now, guys, this is crucial, and I should probably have mentioned this on the last one. The first thing you need to do above all is identify that this is an alternating series, right? Because the only way you can use the alternating series test is if it is an alternating series. And would you guys agree that -1 to the end, this is going to flip back and forth between positives and negatives? And we could list out some terms, but can we just move on? So how much do we have to establish? How many things do we have to show to figure out if it converges? We've got 2 things here, right? Let's go ahead and I'm going to kind of go backwards now. Let's see if we can show if a to the a sub n plus 1 term is less than or equal to the a sub n. Let's go ahead and start with that. Okay. So I need to show that 3 times the quantity n plus 1 over 4 times, oh, I did it again. Four times n plus 1 minus 1 is less than 3n over 4n minus 1. That's what I want to show. That's what I want to, and technically, I guess I need to maybe even write it like this, right? We don't know that that's true. We're kind of determining if it is. So we're just going to cross multiply here a little bit, right? So let's go ahead and clean that up. So that'd be what? 3n plus 3 over, that'd be 4n. And then that'd be plus 4, but minus 1. So I think that'd be a plus 3. Is that plus 3? If you have 4 minus 1, that'd be plus 3. Less than or equal to 3n over 4n minus 1. That doesn't really help us out too much. Now let's go ahead and cross multiply here. So I'm going to be careful. I think I'm going to get 12n squared. Got to do FOIL here. Then outside that'd be minus 3n plus 12n minus 3. I foiled in my head there. Hopefully you can let me know if I screw that up. The other side's going to be a little bit easier. 12n squared plus 9n. Okay. Now note that those 2 guys together there, those are 9n. Would you agree? So what cancels? Everything except for that minus 3. So you're left with -3 less than or equal to what? A 0. Would you guys agree that -3 is less than or equal to 0? Great. Looking good. So we have just taken care of this requirement right here, that first requirement in this particular rendition of that theorem. Let's go and look at the second requirement. And the second requirement, if I'm not mistaken, is to show that the limit as n goes to infinity of a sub n has to equal 0. In other words, as this thing goes on, we need to know that we're essentially adding nothing at the end of this thing. So we need to do the limit. In fact, let me put a little question mark there, right? A little question mark there. N goes to infinity. Now here we're just doing a sub n, so we got to do 3n over 4n minus 1. Uh-oh, what's that number? 3/4. By the way, let me do this in red. So what can we conclude? Well, first of all, we can say that the alternating series test does not apply, so maybe I should write that first. AST does not apply. That's the first thing. But what does this tell us? Has to diverge, because why? That's the divergence test. The divergence test actually does apply to alternating series as well. So this one is going to diverge.
Can you just write the divergence to the divergence test?
Yep. Guys, there's no way this guy's going to converge because essentially at the end, we're going to be adding 3/4, minusing 3/4. Adding 3/4, minusing 3/4. Adding 3/4, minusing 3/4. So it's going to alternate at infinity, which means the limit of this thing is not a single value, it's two values, and therefore it's not. Yes, kind of. Yeah, Gavin. Yes. Yeah, I'll talk about that more later. Maybe we'll see. Okay. Gavin, just to throw it out, I have seen sines and cosines in series that will act like hidden alternators. All right. Okay, so you've got kind of a feel for the alternating series test. I did an example where it worked, and I've done an example where it didn't quite work, just so you would see that. So now I want to talk about estimating sums. This is where it gets a little bit more complicated. It says a partial sum, S sub n, of any convergent series can be used to approximate the total sum of S, which I think we've already talked about that. But this is not much use unless we can estimate the accuracy of that approximation. Now I'm hoping that this right here looks familiar to you guys. Let me write that maybe here in red. The remainder of the nth term of a series is equal to the actual sum of the thing minus the partial sum. We've talked about that equation before. I don't remember if it was last, I feel like it was the week before last, but I can't remember. The next theorem says that for a series that satisfies the conditions of the alternating series test, the size of the error is smaller than the next term, which is the absolute value of the first neglected term. Now, in our textbook, it will refer to this as the alternating series remainder theorem. This particular book, which is actually made by the same author, but it's a different book, is the alternating series estimation theorem. They're the same thing. This one's, the remainder is what we're talking about here. We're talking about how far off are we from the actual answer. And so instead of using remainder, they're just using the word estimation. So it says if the sum, by the way, that's capital S. So this is the actual sum. Not accurate, actual. That's just a U. If the actual sum of that series, where B sub n is greater than 0, is the sum of an alternating series, and it satisfies this and this, which we've kind of already discussed, means it's convergent, right? So this is essentially saying, if this is convergent, which that should make sense by the use, then the absolute value of the remainder of the nth terms is equal to the actual sum minus the partial sum absolute value. And all of that has to be less than the B sub n plus 1 term. Now again, this piece up here, this is just kind of the if of the if-then part, and that kind of makes sense. So basically we're talking about an alternating series that converges. That's what this stuff is, it converges. This is what we can use. And really it's this piece right here that's going to be very helpful. Okay, wow, that was pretty amazing, Mr. Hunt. That just totally made that presentation. So let's go ahead and look at an example here. It says, approximate the sum of this series by its first 6 terms. Now, would you guys do me a favor? Would you get your calculators going? If you don't have your calculator, it's okay. But here in a minute, I'm going to ask you to, I'm just going to ask you, I'll just tell you right now what I'm going to ask you if I can ever get this thing to actually write without adding extra stuff on it. I'm going to ask you in just a second, and hopefully you'll already have it done, so it's no surprise. What is the partial sum for the first 6 terms. And you should be able to just plug that right there in your calculator using Math 10, I think it is. Anyways, so I'll come back to that. What I'm going to do up here right now, just for the novelty of it, is I'm actually going to write the first 6 terms. So what did you get for your partial terms there, your partial sum, the first 6? What did you get, Jack? Oh, no calculator, okay. You can't do that in your head? Jen, we're just adding negative 1 plus 1 over 2 radical
1
2.
over 1,000.
James, Lynn, did you have to get that? Huh? Mason?
Negative 0.7353.
Now, guys, I'm writing it out a little bit further, but that's exactly what Mason said. The other thing I need to make sure I say right now, is this the exact partial sum? Is this the exact, this is not, correct? The clue is you've got these radicals in here, so this would actually technically go on. However, here's an important thing for you to think about. This is the first 6 terms. This series goes on forever. Is this S? Is this equal to S? No, it is not. So the question is, and that's the whole point of this theorem, is how accurate is this approximation? That's what we're trying to figure out. So I'm going to put no, even though I put dot, dot, dot here. This is only the first 6 terms. By the way, would you guys all agree that if we did more terms, that the accuracy would get better, right? But we're just going to use these first 6 terms. And the next thing that I want to ask you is, what is a sub 7? Notice I said A, not S. How would you find a sub 7? Just plug in 7 right there. By the way, is it going to be positive or negative? I think it's going to be negative, isn't it? So you would basically do negative 1 divided by 7 radical 7, and you will get 0.053994247. Okay, so this is the, let me make a couple of notes here. This is the partial sum for 6 terms. And then this guy here, this is the 7th term. Okay, by the way, it would go on as well, right? So now I want to go back. So are we all okay? Does this kind of, I know that doesn't seem like I've done much, but what I have done is this. I have found the partial sum basically using my calculator, and I got this value, and I've got that the 7th term of that series is this number right here. Now I'm going to go back to this theorem, and the theorem should make sense, I think. It's saying that the remainder, that's the remainder, by the way, we're talking about the absolute value of the remainder. The remainder has to be equal to the actual sum minus the partial sum, which again, I think that makes sense. If I added more terms to this S sub n, it's going to get more and more close to the actual S, which means this remainder is going to go to a 0, right? But here's the key part. I'm telling you that the error has to be less than this. In fact, let me write that. The error has to be less than this. In other words, negative 0.78929 less than S, less than 0.68131. And I have rounded those. Please just write that down and then I'll explain what that means. And be careful here. Remember, we're dealing with negative numbers. So the magnitude of this number is bigger than the magnitude of this one, but since we're dealing with negative, this one's more negative than that one. Does that make sense? Okay. But sometimes people kind of forget about that. Okay, so here's how I finish this off. This theorem basically tells me my error, the amount I'm off, is based on the next term in the sequence. So when I got this answer here, this was an approximate answer for the sum. This answer is at most off this much. So if I add this to this, that gave me the negative 0.78929. Does that make sense? If you take these two negative numbers and add them together, you will get this negative number. But remember, we are dealing with absolute value. Okay, I'm going to go back again. Remember, these were absolute values. Since it's absolute value, it means that I would have to add this amount instead of subtracting, if you will. So this would become a positive amount of error. So if I put a positive amount of error, I'm going to get that negative 0.68131. And by the way, I guess one final comment I should make here. That's about 1/20th. Oh, not 1/20th. Is that right? No, that's right. Okay. Because this would be tens, hundreds. 5 over 100 is 1 over 20, right? So I'm telling you that this partial sum is at most off by 1/20th of a decimal. Okay? 1/20th. So the actual sum, which we have not calculated, in fact, that's a P series, isn't it? It's not geometric. So I don't know that we can get the exact value, but we know that we're no more than a 20th off. So the actual sum has to live between those two values. I'm telling you, there's no way that this sum is 0.8 negative. It cannot be negative 0.8. You know why it can't be negative 0.8? Because negative 0.8 is not between these two decimals. Does that make sense? And by the way, again, if I needed more accuracy, what would I do? Just do a couple more terms, and they'll get me more and more accurate. So that's how, if a question ever says, hey, I want you to find, this portion, I want you to find this sum and be within 1/100th of a unit accurate. Well, then you can figure that out, right? And the way you would do that is just look by the accident term. Okay, I'm going to stop there on that example. Comments or questions on that one? I know that one was a little bit more difficult. Maybe, I don't know. That makes sense? Thanks, Gavin. Appreciate you shaking your head. It's good feedback. Okay, so last comment here, and where are we at here? 9:36. Okay, good, perfect. We got 9 minutes left, so this will let me get to this last thing. And the last thing is actually, we've actually already talked about the last concept, and you'll see. I'll get to that in just a second. So let's go ahead and finish this off. Remember, objective number 1 was to be able to apply the alternating series test, which we did in that those first two examples, although one of them didn't work. This third example was to basically estimate an approximation or figure out how accurate it is. So our third thing, and I'm going to skip over that. Our third thing is to determine whether a alternating series is absolutely convergent or conditionally convergent. And here it is. the sum of a sub n is absolutely convergent if the sum of the absolute value of a sub n is convergent. Let me say that again. A series is absolutely convergent if the absolute value of a sub n, the sum of that, is convergent. Yes? I'm going to I'll show you. It means literally absolute value of it. Okay, I'll show you an example. A series is said to be conditionally convergent if the sum of a sub n converges, but the absolute value of a sub n does not converge. Yes?
What if a sub n diverges, but the absolute value converges?
Okay, hold on, let me think about that. Say that one more time.
Summation of a sub n diverges, but the absolute value converges. Or does that never happen?
It does. Hold on. We'll get to that. You're going to see in my example. Okay? Now, guys, before I move forward, let me just tell you, what we're getting ready to do here, in essence, is going to be could be a question, and in fact, I'm pretty sure it will be on the BC exam. Somewhere in the exam, they're going to say, determine if it's convergent, absolutely convergent, or conditionally convergent. So it's going to be a kind of a yes/no question, all right? And you might say, well, Mr. Brown, that seems kind of, why, who cares? It turns out when you go to higher level calculus classes, some of these series, this is obviously, let me just say, this is a stronger, or let me say better, maybe that's a better way. This is a better series. If a series is absolutely convergent, that's actually better than conditionally convergent. It's stronger, if you will. Does that make sense? And there's certain higher level calculus concepts that we'll say in the conditions, we'll say, if the series is absolutely convergent, blah, 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 blah. Which means if it's not absolutely convergent, if that theorem may not apply. All right, so let's look at this example. It says determine if the series converges absolutely or conditionally. Okay, so first of all, let's see, well, let's go back to our definition. Here's our definition. It absolutely converges if the absolute value converges, and it's going to be conditionally convergent if the a sub n converges, but the absolute value does not, or the absolute value of the sum diverges. So let's just go ahead and write this a few of these terms out. So n is 1, right? So if n is 1, that's going to be 1 minus 1, which is 0, which is negative 1 to the 0 is, I think, 1. And then, of course, 1 squared is 1. The next term is going to be negative, right? Because now we're putting in 2. So 2 minus 1 is 1. Negative 1 to the 1 is negative. And then, of course, then if I'm putting in 2, that'd be what, 1/4? The next term is going to be positive. And that's going to be 1/9. Next one. 1/16. And let's do one more. 1/25. So sometimes it's helpful just to kind of see what you're dealing with. So this is the series we're talking about. And we want to determine if it is absolutely or conditionally convergent. So let's go ahead and do the following. Let's look at the following. Absolute value of negative 1 to the n minus 1 over n squared. So when I do the absolute value, what's the only thing absolute value does? It gets rid of anything that's negative. In other words, guess what it does to the alternator? Unfortunately, it kills the alternator. So that's bad. I mean, it sounds bad. So we're essentially dealing with this now, right? Which is this is a P series. What is P here? Which is greater than 1, so it is convergent. You guys agree? Now let's go back to our previous slide. If the sum of a sub n is absolutely convergent, if the sum of the absolute value of a sub n converges. The sum of a sub n is conditionally convergent if the sum a sub n converges, but the sum of the absolute value of A sub n diverges. So guess what, guys? This is absolutely. I'm not gonna fix it this time. It's absolutely convergent. Okay. Final example. Ooh, timing is really good. This should look familiar. Let me write it out. Starting with 1, what's the first term? Just 1. Second term. Third term. Plus 1/3. Next term. Oh, wow. Have we seen this one already? What is this called? Alternating harmonic series, which we have already shown. So if you guys don't mind, I'm not going to go back and redo this problem. I think it was example 1. Example 1, we showed that this was a convergent series, correct? Okay, so in other words, we have shown that the sum of n equaling 1 summation of A sub n converges, right? We've already done that. Now, in order to do absolute versus conditional convergence, what do we need to do? Now we need to do the absolute value of this, right? By the way, what's the absolute value do to the alternator? It kills it. So sad. So frustrating. You guys probably think I'm unbelievable. I can't hardly even write on here. What's that? That's the harmonic series. We already know that that goes to infinity. It diverges because that's the harmonic series. This is the harmonic series. Okay, now I'm going to jump back 2 slides. A series is absolutely convergent if the sum of the absolute value of A sub n converges. We saw that in example 4. The sum of a series, the series, is conditionally convergent if the series itself converges, but the sum of the absolute value of A sub n diverges. That's what we're dealing with here. So this is going to be conditionally convergent. So let me say this to let me make this as clear as possible. In fact, let me go back to the previous example. This series converges and converges absolutely. What I'm telling you is this converges if I don't get rid of the plus minus stuff. It converges if I do get rid of the plus minus stuff. Either way, it converges, so we say it's absolutely convergent. However, this is the classic case. This particular series, if I do the absolute value of it, which gets rid of the alternator, this diverges. But if I leave the alternator alone, we've just seen earlier today that it did converge. We call that conditionally convergent. It converges only in the case where we don't get rid of that alternator. If that alternator is gone, like down here, divergent. So this is what I kind of mentioned earlier today. I kind of said the fact that, hey, we already knew that the harmonic series diverges. And then I asked you earlier today, what about this alternating harmonic series? Do you think it converges or diverges? And I think Jack said he thought it did converge, and he was right. But it only converges. Anyways, that's it. So that brings us right to the 60 minutes. I've actually got an exit ticket for you guys. I will take questions. We're going to kind of get into the 30 minutes of support time. But I would love for you to finish the class out by giving me some feedback on the lesson. Please do your best. This isn't for a grade, but it just gives me feedback on how I did. And I appreciate your guys' patience. So at this point, once you get the exit slip done, the last 30 minutes of this class is up to you. If you want to stick around and ask me questions, that's fine. If you want to start working on homework and stay online and ask, that's fine. If you need to log off because you got to, eat breakfast or whatever, that's fine too. So I'm going to mute myself. Please hit something in the chat though if you have a comment or a question or if you need anything from me.
Hold on a second.
Hold on, yeah, wait for them to do it.
I have to read.
No,
Yeah,
it's
that's
okay. It's okay.
All right, I'll get it.
So what happens if, what happens if A sub N diverge? Is that even possible?
Okay, so coming back to your question, and maybe I misunderstood it, but I thought you were talking about this.
No.
So let me make sure I understand. You're saying, what if this diverges, but this converges?
Yeah.
Not possible.
I was just making sure.
In fact, there's a exit slip question kind of based on that.
What would the limit goes to zero, the limit equals zero?